There's a place in the universe that shouldn't exist. A region so vast and empty that it defies our understanding of how the cosmos actually works. Scientists call it the cold spot, and it's lurking in the constellation Eridanus, about 3 billion light-years from Earth. Imagine standing in complete darkness. The kind of darkness where you can't see your hand in front of your face. Now imagine that darkness stretching for nearly 2 billion light-years in every direction. That's what we're dealing with. Except this isn't just empty space between galaxies. This is a hole in the universe so profound that when light from the Big Bang passes through it, something strange happens. The light loses energy. It gets colder. And what we're left with is a cosmic anomaly that challenges everything we think we know about the structure of reality itself. The story begins in 2004. NASA's Wilkinson Microwave Anisotropy Probe, a satellite designed to map the oldest light in the universe, detected something unexpected. In one particular patch of sky, the temperature of the cosmic microwave background radiation was significantly colder than it should be. Not just a little colder. About 70 microkelvin colder than the surrounding regions. Now you're probably thinking, 70 microkelvin doesn't sound like much. And you'd be right to think that. We're talking about a temperature difference smaller than anything you could ever feel. But here's what matters. In the cosmic microwave background, the typical temperature variations are only about 18 microkelvin. This cold spot was nearly 4 times larger than normal fluctuations. In some regions, it reached 140 microkelvin below average. The cosmic microwave background itself is something extraordinary. When the universe was only 380,000 years old, it was about 1 million times smaller than today and had a temperature exceeding 10,000 kelvins. The entire cosmos was filled with a dense plasma of electrons and atomic nuclei. Then, as expansion continued, everything cooled down. The plasma became neutral atoms. And at that precise moment, light was released in a flood of white-hot radiation that has been traveling through space ever since. That radiation is what we call the cosmic microwave background. It's been stretched by the expansion of the universe from visible light into microwaves, and it's cooled to a temperature of just 2.7 Kelvin. When you look at the CMB, you're seeing a baby picture of the universe. A snapshot from when our cosmos was still in its infancy. The CMB is almost perfectly uniform. Almost. There are tiny temperature differences, about 1 part per million, scattered across the entire sky. These imperfections are crucial. They represent quantum density fluctuations from the very early universe. Regions where matter was slightly more or slightly less densely packed. Over billions of years, those tiny differences would grow into the massive cosmic web we observe today. Galaxy clusters, filaments of dark matter, and voids. But the cold spot was different. It wasn't just another small fluctuation. This thing spans roughly 10 degrees across the sky, covering an area about 20 times the width of the full moon. When cosmologists ran statistical analyses, they found something disturbing. The probability of this feature appearing by random chance in the standard model of cosmology was less than 2%. Some calculations put it much lower. Think about what that means. You're looking at the most detailed map of the early universe ever created, and there's a feature that statistically shouldn't be there. It's like finding a massive dent in an otherwise perfectly smooth ball. The question becomes, what caused it? For several years, scientists debated whether the cold spot was even real. Maybe it was just an instrumental error. Maybe the WMAP satellite had a glitch. But in 2013, the European Space Agency's Planck satellite, a completely independent instrument with different technology, observed the same feature at similar significance. The cold spot wasn't a mistake. It was genuine. So cosmologists needed an explanation. The standard theory says that tiny quantum fluctuations during cosmic inflation, a period of exponential expansion in the first fraction of a second after the Big Bang, created all the temperature variations we see in the CMB. Randomly big cold spots should appear occasionally. But this one was so large and so cold that calling it a random fluctuation felt like calling winning the lottery 5 times in a row lucky. That's when researchers started looking for alternative explanations. What if the cold spot wasn't created during the Big Bang at all? What if something between us and the CMB was causing the temperature depression? Enter the Integrated Sachs Wolfe effect. This is where things get interesting. When photons from the cosmic microwave background travel through the universe, they pass through regions of varying density. Galaxy clusters, filaments, and voids. As light enters a void, it must climb out of a gravitational potential well. Normally, when light falls into the well, it gains energy. When it climbs back out, it loses that energy. The two effects cancel out perfectly. But here's the critical part: that only works in a static universe. Our universe is not static. It's expanding. And that expansion is accelerating due to dark energy. When light enters a void at one time and exits later, the void has evolved. It's gotten deeper because dark energy is stretching space itself. The gravitational potential has changed between entry and exit. The result? The photon exits with less energy than it had when it entered. Less energy means a longer wavelength. A longer wavelength corresponds to a colder temperature. This is the Integrated Sachs-Wolfe effect, and it's intimately connected to dark energy. Without accelerated expansion, the effect wouldn't exist. So the hypothesis formed: maybe there's an enormous void in the direction of the cold spot. A region of space with significantly less matter than average. If CMB photons passed through this void, they'd lose energy through the Integrated Sachs-Wolfe effect, appearing colder when they reached Earth. But for this explanation to work, the void would need to be truly massive. Not just large. Colossal. Typical cosmic voids are a few hundred million light-years across. To create the observed temperature depression, you'd need something perhaps 1,000 times larger in volume. A void 6 to 10 billion light-years away and nearly a billion light-years across. The problem? Voids that large shouldn't exist according to our models of structure formation. Creating such a massive underdensity would be even more improbable than the cold spot itself appearing as a primordial fluctuation. Trading one statistical nightmare for another doesn't solve anything. Yet in 2015, something remarkable happened. A team led by Istvan Saputty at the University of Hawaii combined observations from the Pan-STARRS-1 telescope on Maui with data from NASA's Wide Field Survey Explorer satellite. They were mapping the three-dimensional distribution of galaxies in the direction of the cold spot. What they found was staggering. There was indeed a supervoid. An enormous region of space, centered about 3 billion light-years from Earth, stretching 1.8 billion light-years across. The void contained roughly 30% less matter than the surrounding cosmic web. Saputty described it as the largest individual structure ever identified by humanity. The discovery sent ripples through the cosmology community. Finally, a physical explanation for the cold spot. The supervoid's existence was later confirmed by the Dark Energy Survey, which used gravitational lensing to map dark matter distribution. When massive structures warp spacetime, they bend light from more distant galaxies. By measuring these distortions, astronomers created a dark matter map. The Eridanus supervoid appeared as the most prominent underdensity in the entire data set. Everything seemed to fit. The cold spot aligned with the supervoid. The supervoid was real, confirmed by multiple independent observations. Case closed, right? Not quite. Because when cosmologists calculated how much cooling the supervoid should produce through the integrated Sachs-Wolfe effect, they hit a wall. The maximum cooling predicted was about 20 microkelvin. The cold spot shows 70 microkelvin of temperature depression on average, with some regions reaching 140 microkelvin. The supervoid could only account for 10 to 20% of the observed anomaly. The numbers didn't add up. Even with the largest void ever discovered sitting directly in the line of sight, the standard model of cosmology couldn't explain what we were seeing. Either we were witnessing an incredibly improbable coincidence, a primordial cold spot from the Big Bang that just happened to align with a massive supervoid, or something was fundamentally wrong with our understanding of how the universe works. And that's where the real mystery begins. Word count, 1667. The discovery sparked a new question. What if the supervoid itself was behaving strangely? When the Dark Energy Survey team examined their gravitational lensing data more closely, they found something peculiar. The lensing signal from the Eridanus supervoid was roughly 30% weaker than it should be. Computer simulations of void formation consistently predicted a stronger signal. The actual observations didn't match. This wasn't a small discrepancy you could wave away with measurement error. Multiple independent analyses confirmed it. The void was deflecting light less than expected, suggesting it contained more mass than the galaxy counts indicated. Or perhaps the void had evolved differently than standard cosmology predicts. Here's where things get interesting. A weaker lensing signal could mean the void has become shallower over time, less deep gravitationally. If that's true, the integrated Sachs-Wolfe effect would actually be stronger, not weaker. Photons would lose more energy traversing a void that's actively becoming shallower as they pass through. Suddenly the math changes. Maybe the supervoid could explain the cold spot after all. But only if our cosmological model is wrong about how voids evolve. Dark energy enters the picture again. The mysterious force accelerating the universe's expansion doesn't behave uniformly everywhere. In dense regions, gravity dominates. In vast empty spaces like supervoids, dark energy might have disproportionate influence. If dark energy is stronger or operates differently in these cosmic deserts, voids would evolve faster than our models predict. That's a profound implication. It would mean Lambda CDM, the standard model of cosmology, needs modification. Not a complete overhaul, but a recalibration of how dark energy interacts with large-scale structure. Some researchers find this possibility compelling. Evidence from other distant supervoids hints at similar anomalies. The cold spot might not be unique, but rather the most obvious example of a phenomenon we've been missing. Others remain skeptical. One anomalous lensing signal isn't enough to rewrite cosmology. Statistical flukes happen. Maybe we're just looking at the tail end of probability distributions, seeing something rare but not impossible. The debate intensified when spectroscopic surveys painted a more complex picture. These surveys measure galaxy distances with extreme precision, creating three-dimensional maps of cosmic structure. When astronomers aimed these instruments at the cold spot region, they found something unexpected. There wasn't one clean supervoid. Instead, they detected voids at multiple distances. one at roughly 460 million light-years, another at 850 million, a third at nearly 1 billion light-years away. Between them, small overdensities, clusters of galaxies interrupting the emptiness. This fragmented structure complicated everything. Could multiple smaller voids collectively produce the cold spot through the integrated Sachs-Wolfe effect? The calculation suggested no. The cumulative cooling still fell short. But here's the twist. When researchers examined a control region in another part of the sky, they found a similar void structure. Galaxy distribution almost identical to the cold spot direction. Yet that region showed no temperature depression in the CMB whatsoever. Two nearly identical lines of sight through cosmic structure. One produces a massive cold spot. The other produces nothing unusual. That observation alone challenges the supervoid explanation. If voids cause the cold spot, why doesn't the other void create a similar feature? The simplest interpretation: the cold spot is primordial. It originated in the first fraction of a second after the Big Bang, imprinted during cosmic inflation. The supervoid is real but irrelevant. Just an unfortunate coincidence making us chase the wrong explanation. Except coincidences this extreme are statistically troubling. Having both a rare primordial anomaly and the largest known void aligned perfectly stretches credibility. It's possible, certainly. The universe doesn't care about our intuitions. But it demands we look harder for connections. That's when the truly exotic explanations emerged. Ideas that push beyond conventional physics into speculative territory. Some physicists proposed cosmic textures. These are topological defects in spacetime itself, remnants from phase transitions in the extremely early universe. Imagine the fabric of space nodding or twisting in specific regions as the universe cooled and changed state. A cosmic texture could create localized temperature variations in the CMB. The math works. The scale could be right. But textures are purely theoretical. We've never definitively observed one. Invoking them to explain the cold spot feels like replacing one mystery with another. Even more speculative, cosmic strings. One-dimensional defects in spacetime, potentially formed during symmetry breaking in the first moments after the Big Bang. A cosmic string loop could produce CMB anomalies as it evolved and eventually decayed. Again, possible in principle. Lacking in observational evidence. Then there's the multiverse hypothesis. Laura Mersini-Houghton proposed that the cold spot might be the signature of another universe. Before cosmic inflation separated distinct bubble universes, quantum entanglement could have linked them. When inflation drove the bubbles apart, that entanglement might have left an imprint. A bruise on our cosmic horizon where we briefly touched another reality. If you think that sounds far-fetched, you're not alone. It's an extraordinarily bold claim requiring extraordinary evidence. But the cold spot combined with certain theoretical models of eternal inflation makes the idea at least worth examining. Some researchers have explored whether bubble collisions during the inflationary epoch could produce the observed pattern. The challenge with all these exotic explanations is testability. How do you prove a cosmic texture exists? How do you confirm contact with another universe? These ideas live in the uncomfortable space between theoretical possibility and observational verification. A more recent proposal takes a completely different approach. What if the cold spot isn't distant at all? Several researchers investigated whether foreground galaxies, relatively nearby structures between us and the CMB, could be responsible. The Eridanus supergroup sits in the cold spot direction. It's the largest galaxy group complex in our local cosmic neighborhood. Predominantly spiral galaxies, which behave differently from ellipticals in certain ways. When these researchers cross-correlated galaxy positions with CMB temperature maps, they found something intriguing. There's a systematic temperature decrease around late-type spiral galaxies. The effect extends several megaparsecs. The physical mechanism isn't fully understood yet. Possibly related to how these galaxies interact with the CMB photons through scattering or absorption. When they modeled this foreground temperature profile for the entire Eridanus supergroup, the resulting pattern closely matched the cold spot's shape. This explanation has appeal. It's local, testable, and doesn't require exotic physics. The Eridanus supergroup's unusual concentration of spiral galaxies could naturally produce the observed temperature depression. The coincidence of this unique galaxy complex sitting in the cold spot region adds weight to the hypothesis. But questions remain. The temperature decrement mechanism around spiral galaxies needs better theoretical grounding. And would this local effect really mimic a feature that appears primordial in its statistical properties? The debate continues. What's remarkable is how many plausible explanations exist. Primordial fluctuation. Supervoid integrated Sachs Wolfe effect. Modified dark energy. Cosmic textures. Multiverse collision. Foreground galaxies. Each has supporting evidence. Each has problems. The cold spot refuses to yield a clean answer. Every new observation adds information while somehow deepening the mystery. Confirmations create new puzzles. Solutions reveal inconsistencies. Perhaps that's the real lesson here. The universe doesn't package its mysteries neatly. Nature doesn't arrange evidence to make our theories obviously right or wrong. Sometimes the data genuinely sits in ambiguous territory where multiple interpretations remain viable. What we know for certain, the cold spot exists. It's statistically significant. The Eridanus supervoid exists. It's aligned with the cold spot. The supervoid alone can't explain the full temperature depression under standard cosmology. The lensing signal from the void is anomalously weak. Foreground galaxies show unexpected temperature correlations. What we don't know, which of these facts matter most? Whether they're connected or coincidental. If our cosmological model needs adjustment or if we're just witnessing rare but allowed phenomena. The cold spot has become a testing ground. Different approaches, different assumptions, different conclusions. Some see evidence for new physics. Others see statistical noise amplified by confirmation bias. The data supports both interpretations depending on which pieces you emphasize. This ambiguity frustrates some cosmologists while energizing others. It's exactly the kind of anomaly that could reveal something profound about how the universe works. Or it could dissolve into mundane explanations once we gather better data. Future observations will help. Next-generation CMB experiments will map temperature fluctuations with unprecedented precision. Deeper galaxy surveys will characterize the three-dimensional structure in the cold spot direction more completely. Improved gravitational lensing measurements will constrain the void's properties. But for now, the cold spot remains what it's been since its discovery. A question mark written across the sky. A challenge to our understanding. A reminder that the cosmos still holds secrets we haven't unraveled. And there's something else. The cold spot isn't alone. Several other anomalies riddle the CMB, and they share an unsettling characteristic. They align. Cosmologists call it the axis of evil. Not because it's malevolent, but because it shouldn't exist. The cosmological principle states that the universe should look statistically identical in all directions. No preferred orientation. No cosmic up or down. Yet multiple large-scale features in the CMB appear oriented along a particular axis through space. The cold spot is part of this pattern. So is the quadrupole moment, one of the CMB's fundamental harmonic components. The octopole too. These features align with each other and with the plane of our solar system in ways that seem impossibly coincidental. When you run simulations of random CMB fluctuations, this kind of alignment almost never appears. Less than 1% chance. Some analyses push that probability even lower. We're either witnessing an extraordinary statistical fluke, or something fundamental is wrong with our assumptions. The Northern Hemisphere has its own cold region. Computational analysis using Kolmogorov complexity found evidence for a northern cold spot with statistical properties remarkably similar to its southern counterpart. The southern anomaly shows stratification expected for voids. The northern one exhibits nearly identical randomness characteristics. But here's where it gets messy. Different statistical methods fail to confirm each other. One analysis technique finds the northern cold spot significant. Another finds it marginal. A third sees nothing unusual. This inconsistency plagues CMB anomaly research. The features hover at the edge of statistical significance where methodology matters enormously. Are these alignments telling us something profound about the universe's structure? Or are we pattern matching noise? The human brain excels at finding patterns, even in random data. Give statisticians enough freedom to slice and analyze data different ways, and they'll eventually find something unusual. The question is whether these anomalies survive rigorous testing or dissolve under scrutiny. Some physicists propose radical explanations. Maybe our observable universe has unusual geometry or topology. Perhaps we're seeing effects from the pre-inflationary universe, hints of what existed before cosmic expansion erased most information about the very early cosmos. Laura Mersini-Houghton offered one of the boldest interpretations. She suggested the cold spot could be the imprint of another universe beyond our own. Quantum entanglement between universes before cosmic inflation separated them. If true, this would be the first direct evidence for the multiverse. The multiverse hypothesis states that our universe is one bubble in an infinite sea of universes. Each bubble potentially has different physical laws, different constants of nature. During the earliest moments after the Big Bang, if our cosmic bubble collided with another, it could leave a signature. A bruise on the CMB. This idea sounds like science fiction, but it emerges from serious theoretical physics. Eternal inflation theory naturally produces multiple bubble universes. The mathematics works. The question is whether nature actually implements this solution. Testing such claims presents obvious challenges. We can't visit other universes. We can't rerun the Big Bang to see if collisions happen. We're stuck analyzing subtle patterns in ancient light, trying to distinguish genuine cosmic scars from statistical noise. Other exotic proposals exist. Cosmic textures, remnants of phase transitions in the early universe. These are topological defects where spacetime itself has unusual properties. Think of them as frozen imperfections in the fabric of reality, formed when the universe cooled and transitioned between different quantum states. Cosmic strings represent another possibility. Theoretical one-dimensional objects with enormous energy density. If a cosmic string loop existed in the early universe and underwent a process called thawing, it could produce temperature patterns resembling the cold spot. These explanations share a common thread. They invoke physics beyond the standard cosmological model. New phenomena that don't appear in our current best theory of how the universe works. This makes them simultaneously exciting and suspect. Exciting because discovering new physics would be revolutionary. Suspect because extraordinary claims require extraordinary evidence. The challenge facing cosmologists is determining which anomalies are real signals and which are artifacts of our analysis methods. When you're looking at the entire sky's worth of CMB data, you have millions of pixels. Run enough statistical tests, and some will show unusual results purely by chance. This problem intensifies when dealing with large-scale features. There aren't many independent large-scale regions in the observable universe. Limited sample size means limited statistical power. Finding one weird cold spot in the only universe we can observe doesn't tell us much about whether such features are truly anomalous. Imagine flipping a coin 10 times and getting 7 heads. Somewhat unusual, but well within normal probability. Now imagine you only get to flip the coin once, and you need to determine if it's fair. Impossible task. You need many trials to establish statistical patterns. The universe provides only one cosmic microwave background. Despite these challenges, the alignments persist across different analysis methods and datasets. WMAP saw them. Planck confirmed them. Multiple research groups using different techniques reach similar conclusions. The axis of evil refuses to disappear. Some cosmologists argue we should take these anomalies seriously as potential evidence for new physics. Others maintain their statistical flukes amplified by confirmation bias and publication incentives. Positive results get published. Negative results often don't. This creates a literature skewed toward finding anomalies. The truth probably lies somewhere in the middle. Some anomalies will dissolve with better data and more careful analysis. Others might prove robust and demand explanation. Distinguishing between these categories requires patience and rigor. What makes this frustrating is the time scale. CMB experiments are expensive and take years to complete. Planck launched in 2009 and finished collecting data in 2013. Analysis continued for years afterward. The next major CMB mission might not launch until the 2030s. Progress happens slowly. Meanwhile, theoretical work continues. Physicists explore whether modifications to inflation theory could produce aligned features. Whether dark energy behaves differently on the largest scales. Whether our universe's initial conditions were more special than we assumed. Each possibility opens new questions. If the cold spot comes from modified inflation, what caused the modification? If dark energy varies across space, why? If initial conditions were special, what mechanism selected them? Cosmology deals with unique events. We can't rerun the Big Bang in a laboratory. We can't create experimental universes with different conditions. Our only data comes from observing the one universe we inhabit. This limitation shapes how we approach these problems. The cold spot and its companion anomalies force us to confront fundamental questions about scientific inference. How do we evaluate claims when we can't repeat experiments? What level of statistical significance should we demand when dealing with unique cosmic events? How do we balance openness to new physics against the reality that most anomalies eventually dissolve? These aren't just philosophical puzzles. They affect how cosmologists allocate resources, which theories they pursue, which observations they prioritize. Betting wrong wastes time and money. Betting right could revolutionize our understanding. The conservative approach says stick with the standard model until overwhelming evidence forces a change. Anomalies at the 2 or 3 sigma level aren't sufficient. Wait for 5 sigma certainty or a clear pattern of failures. The progressive approach says investigate anomalies aggressively because they might reveal new physics. Don't wait for ironclad proof. Explore possibilities. Most will fail, but the ones that succeed justify the effort. Both approaches have merit. Both have led to important discoveries historically. The key is maintaining intellectual honesty about uncertainty and avoiding premature conclusions. For now, the axis of evil remains unexplained. Multiple large-scale CMB features align in ways that seem improbable but aren't definitively impossible. The cold spot sits within this pattern, adding its own layer of mystery to an already puzzling situation. Future observations will help. Next-generation CMB experiments will measure polarization patterns with unprecedented precision. These polarization maps provide independent information about the early universe and can test whether the temperature anomalies correspond to genuine physical structures. Improved galaxy surveys will map the three-dimensional distribution of matter more completely. If the cold spot truly connects to the Eridanus supervoid, we should see consistent evidence across multiple observational techniques. If it's a primordial fluctuation, the foreground structure should become increasingly irrelevant as we probe deeper. Gravitational wave astronomy might eventually contribute. If cosmic defects like strings or textures exist, they should produce distinctive gravitational wave signatures. Finding such signals would validate exotic explanations for CMB anomalies. But answers won't come quickly. Cosmology is a patient science. Decades can pass between major observational milestones. Understanding requires building evidence slowly, testing ideas against multiple independent datasets, ruling out alternatives one by one. The cold spot has been known for nearly 2 decades. We still don't have a definitive explanation. The axis of evil has been debated even longer. No consensus has emerged. This timescale frustrates researchers and public audiences alike. Yet this slow progress reflects the profound difficulty of the questions being asked. We're trying to understand the universe's origin, structure, and composition using indirect evidence from ancient light. The fact that we can do this at all is remarkable. So where does this leave us? With a cosmic mystery that refuses simple resolution. A cold spot that might be primordial or might not. A supervoid that might explain it or might not. Aligned anomalies that might reveal new physics or might not. The uncertainty itself tells us something important. The universe doesn't arrange its evidence to make our theories obviously right or wrong. Nature is subtle. Reality is complex. Sometimes the answer is genuinely ambiguous given current data. What happens when we can't resolve an anomaly? When observations point in multiple directions and no explanation fully satisfies? We wait. That's the honest answer most scientists won't give you directly. We wait for better instruments, larger datasets, independent confirmation. The cold spot sits in a peculiar position where it's significant enough to demand attention but ambiguous enough to resist definitive explanation. This creates tension between what we can observe and what we can conclude. Consider the practical realities. Building the next generation of CMB telescopes requires billions of dollars and decades of planning. Launching gravitational lensing surveys demands massive computational resources and international collaboration. Nobody funds these projects to answer a single question. They're designed to probe multiple aspects of cosmology simultaneously. The cold spot becomes one target among many. But here's what makes it fascinating from a research strategy perspective. Even if the cold spot turns out to be a rare statistical fluctuation with no deeper meaning, the process of investigating it drives technological advancement. We develop better analysis techniques. We refine our statistical methods. We build more sensitive instruments. These capabilities then apply to other cosmological questions. The Dark Energy Survey provides a perfect example. Originally conceived to study the accelerating expansion of the universe, it happened to cover the cold spot region. Researchers used its data to probe the Eridanus supervoid not because that was the primary mission, but because the capability existed. This opportunistic science often produces unexpected insights. Gravitational lensing has emerged as one of the most powerful tools in this investigation. The principle is elegant. Massive structures warp spacetime. Light traveling through warped spacetime bends. By measuring how background galaxies appear distorted, we can map the distribution of mass including dark matter that emits no light. When Dark Energy Survey researchers applied this technique to the cold spot region, they confirmed the supervoid's existence with completely independent evidence. No longer relying solely on galaxy counts, they directly measured the gravitational influence of the underdense region. This convergence of multiple observational methods strengthens confidence that the supervoid is real. Yet that same lensing data revealed something unexpected. The gravitational signature appeared weaker than standard cosmological models predict for such a large void. About 30% weaker. This discrepancy could mean several things. Statistical fluctuation remains possible. We might be observing the void at an unusual angle or during an atypical phase of its evolution. Or the void might genuinely behave differently than theory predicts. That last possibility intrigues researchers because it could indicate new physics. If dark energy operates differently in vast underdense regions, our equations need modification. If the void evolved in an unexpected way, our understanding of structure formation requires revision. Small anomalies in data sometimes point toward major theoretical advances. But determining which interpretation is correct requires more data. Always more data. Cosmology progresses through accumulation of evidence, not sudden revelations. Each new survey adds constraints. Each improved measurement narrows the range of viable explanations. The process is methodical, patient, sometimes frustratingly slow. Meanwhile, exotic explanations continue circulating. Cosmic textures. Bubble collisions. Parallel universes. These ideas sound dramatic, and they're not entirely without merit. The mathematics works. The physics is theoretically sound. They just require extraordinary evidence because they invoke extraordinary claims. Cosmic textures arise from symmetry breaking in the early universe. Imagine water freezing into ice. Different regions might crystallize in different orientations. Where these regions meet, defects form. Scaling this up to cosmic proportions, phase transitions in the infant universe could have created topological defects in spacetime itself. A cosmic texture represents one such defect, a region where the fundamental fields never quite settled into alignment. If a texture existed along our line of sight to the CMB, it would create a distinctive pattern. A cold spot surrounded by specific arrangements of hot and cold regions. Researchers have modeled what this should look like. The predicted signature doesn't perfectly match the observed cold spot, but it's close enough to keep the idea alive. Cosmic strings offer another possibility. These aren't strings in the conventional sense but one-dimensional defects in spacetime, unimaginably thin yet containing enormous mass. If a cosmic string loop existed in the early universe, it might have imprinted a pattern on the CMB. Again, the details don't quite fit, but the general concept remains plausible. Then there's the multiverse hypothesis. This one generates the most public excitement and scientific controversy. The idea suggests our universe is one bubble in an infinite foam of universes. During cosmic inflation, different regions inflated into separate universes with potentially different physical laws. If two bubbles collided during inflation, the impact might leave a mark on the CMB. Laura Mersini-Houghton proposed that the cold spot could be exactly such a mark. A bruise from another universe. The mathematics suggests this collision would create a specific pattern, a cold spot with a particular size and temperature profile. The observed cold spot has roughly the right characteristics. But so do several other features in the CMB that nobody considers evidence for bubble collisions. The problem with multiverse explanations is they're nearly impossible to falsify. If we don't see the expected signature, proponents can argue the collision happened differently than modeled. If we do see something, it might still be coincidence. Without independent evidence for the multiverse itself, using it to explain CMB anomalies feels premature. More recently, attention has shifted toward local explanations. What if the cold spot doesn't require exotic physics or distant supervoids? What if nearby galaxies are responsible? This proposal emerged from detailed analysis of how foreground galaxies affect CMB measurements. Researchers discovered that spiral galaxies systematically cool the CMB in their immediate vicinity. The mechanism remains unclear. It might involve dust scattering photons. It might be a subtle effect of the magnetic fields in these galaxies. Whatever the cause, the effect is measurable and consistent. When researchers mapped the distribution of spiral galaxies near the cold spot, they found an unusual concentration. The Eridanus supergroup, one of the largest nearby galaxy complexes, sits directly in front of the cold spot region. Modeling the cumulative effect of all these foreground galaxies produces a temperature pattern remarkably similar to the cold spot. Not identical, but similar enough to suggest this local explanation might account for a significant fraction of the observed anomaly. If correct, this would mean the cold spot is primarily a foreground contamination issue, not a fundamental cosmological feature. This interpretation has appeal. It doesn't require new physics. It doesn't invoke rare primordial fluctuations. It relies on known astrophysical processes operating in an unusual but not impossible configuration. The coincidence of having such a concentration of spiral galaxies in one direction is unlikely but far more probable than many alternatives. However, this explanation faces challenges. The foreground galaxy effect has only recently been characterized. Its physical mechanism remains poorly understood. Applying it to explain the entire cold spot requires assumptions about how the effect scales with galaxy number and distance. These assumptions need verification. Moreover, the foreground explanation and the supervoid explanation aren't mutually exclusive. Both could contribute. The supervoid might create a baseline cooling effect through the integrated Sachs-Wolfe mechanism. Foreground galaxies might enhance this cooling. Together, they could account for the full temperature depression without requiring new physics. Testing these ideas requires improved observations and better theoretical models. Next-generation CMB experiments will measure polarization patterns with unprecedented precision. Polarization provides independent information about the physical processes affecting the CMB. If the cold spot is primordial, its polarization signature should match predictions from inflation. If it's caused by foreground effects or the supervoid, the polarization pattern will differ. The Simons Observatory and CMB S4, both currently under development, will provide this data. These experiments will map the microwave sky with sensitivity far exceeding previous missions. They'll detect features too subtle for current instruments to measure. Within the next decade, we'll have polarization maps detailed enough to distinguish between competing cold spot explanations. Simultaneously, galaxy surveys continue expanding. The Dark Energy Spectroscopic Instrument is mapping millions of galaxies, measuring their distances with high precision. This three-dimensional map will reveal the cosmic web structure in the cold spot direction more completely than ever before. If additional voids exist, we'll find them. If the foreground galaxy distribution has unexpected properties, we'll measure them. Computational cosmology also advances. Simulations now model the universe's evolution from inflation through structure formation with remarkable fidelity. By running thousands of simulated universes and examining how often cold spot-like features appear, researchers can better quantify how anomalous the real cold spot truly is. These simulations also test specific scenarios. What if dark energy behaves slightly differently in voids? What if cosmic strings exist but with different properties than originally proposed? What if foreground galaxies affect the CMB more strongly than current models suggest? Each hypothesis can be implemented in simulation and compared against observations. This multi-pronged approach represents modern cosmology at its best. Theory, observation, and simulation working together to constrain reality. No single measurement provides a definitive answer. Instead, multiple independent lines of evidence gradually narrow the possibilities until only one explanation remains consistent with all data. The timeline stretches across decades. Patience becomes essential. The cold spot has been known for nearly 20 years. It might take another 20 to resolve conclusively. This frustrates those seeking quick answers, but it reflects the profound difficulty of the questions being asked. We're investigating events that occurred billions of years ago, using indirect evidence from ancient light, trying to distinguish between subtle effects that produce similar observational signatures. The fact that we can make progress at all is extraordinary. Yet this patience yields something profound. Every decade brings tools sharper than those before. Every observation constrains the possibilities tighter. The cold spot mystery becomes a lens through which cosmology itself evolves. Consider what we've learned simply by investigating this anomaly. The supervoid's existence is now confirmed through multiple independent methods. Gravitational lensing measurements agree with galaxy surveys. Both show a massive underdensity exactly where the cold spot appears. This convergence of evidence demonstrates the power of modern observational astronomy. Different techniques, different instruments, different analysis methods all point to the same underlying reality. The void itself teaches us about structure formation. Simulations predict voids of certain sizes should exist, but finding one this large in our cosmic neighborhood was unexpected. Does this mean voids grow larger than models suggest? Or did we simply get lucky, observing one of the rare extremes? Statistical analysis helps answer this question. By mapping thousands of voids across the observable universe, researchers build distributions of void sizes. The Eridanus supervoid sits at the tail of this distribution, rare but not impossibly so. About one in several hundred regions of comparable volume should contain a void this large. Given the vast volume of space we can observe, finding one becomes probable rather than miraculous. But the lensing discrepancy remains puzzling. Why does the Eridanus supervoid produce weaker gravitational lensing than simulations predict? Several possibilities exist. Perhaps the void's shape matters more than current models account for. Simulations typically assume spherical voids, but the Eridanus supervoid appears elongated, cigar-shaped. This geometry could affect how light paths bend through the underdense region. Alternatively, the void's density profile might differ from theoretical expectations. Maybe matter isn't distributed exactly as models predict. The void could have internal structure, smaller overdensities and underdensities, creating a complex gravitational landscape. Or perhaps dark energy behaves differently in voids than in average regions of space. This possibility opens fascinating questions. Dark energy constitutes roughly 70% of the universe's total energy density. It drives cosmic acceleration, pushing galaxies apart at ever-increasing speeds. But dark energy's properties remain mysterious. We know it exists through its effects on expansion, yet we don't understand its fundamental nature. Does it interact with matter? Does its density change over time? Different dark energy models make different predictions. In regions of normal density, these differences might be too subtle to detect. But in supervoids, where matter is scarce and dark energy dominates even more strongly, the effects could amplify. If dark energy's influence on structure growth varies with local density, voids would evolve differently than models assuming uniform dark energy properties predict. The weaker lensing signal could indicate such variation. Testing this requires comparing many voids, measuring their lensing signals, and checking for systematic differences from predictions. Current surveys provide enough data to begin this analysis. Early results suggest intriguing patterns, but nothing definitive yet. Meanwhile, the foreground galaxy explanation gains traction. Research teams have now cataloged how CMB temperature correlates with nearby galaxy positions across the entire sky. The effect appears real and reproducible. Late-type spiral galaxies consistently show associated temperature decrements extending several megaparsecs around them. The physical mechanism remains unclear, but phenomenological models can describe the pattern. These models account for galaxy number, density, distance, and morphology. Applied to the Eridanus region, they reproduce much of the cold spot structure. Does this solve the mystery? Not entirely. The models explain the cold spot's shape and location but require fine-tuning to match the observed amplitude. The concentration of spiral galaxies in that direction is unusual but not unique. Other regions show similar galaxy densities without corresponding CMB cold spots. This asymmetry suggests additional factors contribute. Perhaps the supervoid and foreground galaxies work together. The void creates baseline cooling through the integrated Sachs-Wolfe effect. Foreground galaxies enhance this cooling. Combined, they produce the full temperature depression we observe. Separating these contributions requires precise measurements. Future CMB missions will provide polarization data sensitive enough to distinguish different physical mechanisms. The integrated Sachs-Wolfe effect produces specific polarization patterns. Foreground galaxy effects create different patterns. By measuring both temperature and polarization across the cold spot, researchers can determine what fraction comes from each source. This decomposition won't happen quickly. The Simons Observatory begins operations in the mid-2020s. CMB S4 won't achieve full sensitivity until the early 2030s. Analyzing their data takes additional years. We're looking at the 2030s for conclusive results. Galaxy surveys move faster. The Dark Energy Spectroscopic Instrument is already operational, measuring redshifts for millions of galaxies. Within 5 years, it will map the cosmic web structure around the cold spot in exquisite detail. Every galaxy cluster, every filament, every void will be catalogued. If additional structures contribute to the temperature anomaly, we'll identify them. If the Eridanus supervoid has unusual properties, we'll measure them. This comprehensive census eliminates uncertainties about what exists in that direction. We'll finally have the complete three-dimensional picture. Computational advances also accelerate progress. Modern supercomputers run cosmological simulations with unprecedented resolution. These simulations track billions of particles from the early universe through 13 billion years of evolution. They model dark matter, ordinary matter, dark energy, and radiation. By analyzing thousands of such simulations, researchers generate statistical predictions for every observable quantity. How often should voids like Eridanus appear? What temperature decrements should they produce? How should their lensing signals compare to smaller voids? These predictions become testable hypotheses. Some simulations include exotic physics. What if cosmic strings existed during the early universe? What if the cosmological principle is violated on the largest scales? What if dark energy's equation of state differs from the standard assumption? Each variation produces distinct signatures. By comparing simulations against observations, researchers constrain which modifications are viable. Most get ruled out. The universe proves remarkably consistent with simple models. But occasionally, observations hint at deviations worth investigating further. The cold spot exemplifies this process. Initially, it seemed inexplicable, potentially requiring radical new physics. As observations improved, conventional explanations emerged. The supervoid provides a partial explanation. Foreground galaxies might provide the rest. Yet puzzles remain. The lensing discrepancy. The foreground effect's unclear mechanism. The statistical improbability of finding such a large void so nearby. Each puzzle narrows slightly with new data, but none has closed completely. This gradual convergence frustrates those seeking dramatic revelations. No single observation will suddenly explain everything. Instead, the explanation builds incrementally, layer upon layer of evidence constraining possibilities until only one remains consistent with all measurements. It's the scientific method operating exactly as designed, but stretched across decades and involving thousands of researchers worldwide. The human desire for quick, simple answers clashes with nature's complexity. Consider the broader context. The cold spot isn't the only CMB anomaly. The axis of evil, the hemispherical asymmetry, the quadrupole-octopole alignment, multiple features appear statistically unlikely under standard inflation models. Are these connected? Do they point toward common underlying physics? Or are they unrelated flukes, the inevitable result of analyzing data in hundreds of ways until something looks unusual? Distinguishing genuine anomalies from statistical artifacts requires careful analysis. Researchers apply multiple statistical tests, each designed to detect different types of deviations. They also perform blind analyses, deciding on analysis methods before examining results to avoid confirmation bias. The cold spot survives these rigorous tests. It appears in independent datasets from different satellites. It remains significant across various statistical measures. Its alignment with the supervoid provides physical motivation beyond pure statistics. These factors elevate it above mere anomaly hunting. Yet even robust anomalies sometimes disappear with better data. The universe has surprised us before. What seemed like new physics turned out to be instrumental systematics or analysis errors. Healthy skepticism remains essential. Extraordinary claims require extraordinary evidence. For the cold spot, extraordinary evidence is accumulating. The supervoid exists, that's now certain. Its alignment with the CMB temperature depression is real. Whether this alignment is causal or coincidental remains unresolved, but we have the tools to find out. Over the next decade, improved measurements will test every proposed explanation. If the supervoid and foreground galaxies together explain the cold spot completely, we'll know. If additional physics is required, the data will reveal it. Either outcome advances cosmology. Either answer teaches us something fundamental about how the universe works. This is what makes the cold spot fascinating beyond its mysterious appearance. It forces cosmology to sharpen its tools, refine its models, and confront the messy reality of a universe that doesn't always conform to simple predictions. The cold spot is a stress test for our cosmological framework. If Lambda CDM survives this test, our confidence in the model strengthens. If modifications are needed, we discover new physics. Both paths lead forward. What comes next for our understanding of this cosmic mystery? The answer lies in observations already underway and missions launching soon. The Simons Observatory in Chile's Atacama Desert began operations in 2024, deploying next-generation detectors far more sensitive than those aboard WMAP or Planck. Its primary targets include precisely measuring CMB polarization patterns, which encode information about gravitational waves from inflation and the universe's earliest moments. But the observatory will also create the most detailed temperature maps ever produced. Where Planck measured temperature variations to about 10 microkelvin precision, Simons aims for 2 microkelvin. That 5-fold improvement matters enormously when studying a 70 microkelvin anomaly like the cold spot. Higher precision reveals structure within the cold spot itself. Is the temperature depression uniform across its 10-degree span, or does it contain internal variations? Are there smaller hot or cold regions nested within the larger feature? These details constrain formation mechanisms. A primordial fluctuation from inflation should exhibit particular statistical properties. A supervoid-induced ISW effect creates different patterns. Foreground galaxy contamination produces yet another signature. With sufficient precision, we can distinguish these possibilities. The Vera Rubin Observatory, also in Chile, began its legacy survey of space and time in 2025. Over 10 years, it will photograph the entire visible sky every few nights, ultimately detecting tens of billions of galaxies. This unprecedented catalog will map the cosmic web with extraordinary detail, revealing voids, filaments, and clusters throughout cosmic history. For the cold spot specifically, Rubin will identify every galaxy along that line of sight, measuring their distances through photometric redshifts. This creates a three-dimensional map showing exactly how matter is distributed in that direction. Current void measurements rely on surveys covering limited volumes or using less precise distance measurements. Rubin's comprehensive approach eliminates these limitations. If additional voids exist beyond the known Eridanus supervoid, Rubin will find them. If the supervoid has internal structure, perhaps multiple smaller voids aligned by chance, Rubin will reveal it. And crucially, Rubin will map comparable volumes in controlled directions, allowing rigorous statistical comparisons. How unusual is the Eridanus supervoid really? Is it the largest void within 1 billion light-years in any direction, or do similar structures exist elsewhere without corresponding CMB cold spots? Spectroscopic surveys complement photometric studies by providing extremely accurate redshifts. The Dark Energy Spectroscopic Instrument, or DESI, measures spectra for millions of galaxies annually. Its observations already extend through the Eridanus region, and upcoming data releases will contain complete three-dimensional maps of that volume. Spectroscopy eliminates the distance uncertainties inherent in photometric measurements, providing definitive answers about void extent and density contrast. Space-based missions add another dimension. The European Space Agency's Euclid satellite, launched in 2023, combines wide-field imaging with spectroscopy, mapping billions of galaxies across cosmic time. Its gravitational lensing measurements trace dark matter directly, independent of galaxy positions. Remember that the Dark Energy Survey found unexpectedly weak lensing around the Eridanus supervoid, about 30% weaker than simulations predict. Euclid's superior sensitivity and broader coverage will test whether this discrepancy is real or statistical noise. If real, it demands explanation. Does dark energy behave differently in supervoids? Do voids evolve in ways standard models don't predict? NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, brings even greater capabilities. Its wide field of view and infrared sensitivity will map the universe's large-scale structure across vast cosmic volumes. Roman's observations will identify supervoids throughout the observable universe, measuring their statistical properties. How common are structures as large as the Eridanus supervoid? What density contrasts do they typically exhibit? How do they correlate with CMB temperature fluctuations when such correlations can be measured? Building this statistical foundation determines whether the Eridanus supervoid is genuinely exceptional or merely the nearest example of a common cosmic structure. Theoretical work proceeds in parallel. Cosmologists run increasingly sophisticated simulations, modeling how voids form and evolve in universes with different properties. These simulations now incorporate dark energy, dark matter clustering, baryonic physics, and radiation effects. By comparing simulated voids against observations, researchers test whether Lambda CDM predictions match reality in detail, not just broad averages. The lensing discrepancy provides one such test. Simulations predict a certain lensing signal around voids of given size and depth. Observations suggest a weaker signal. Either observations are incomplete, or simulations miss important physics. Some theorists explore modifications to general relativity. Einstein's equations govern gravity across cosmic scales, but they've never been tested in environments as extreme as supervoids, regions where matter density drops far below the cosmic mean across billions of light-years. Perhaps gravity operates slightly differently under such conditions, altering how voids evolve and how they affect passing light. These modifications would have detectable consequences beyond the cold spot, affecting galaxy motions, gravitational lensing, and cosmic expansion. Upcoming observations will test these predictions. Others investigate the foreground galaxy explanation more carefully. If nearby spiral galaxies somehow depress CMB temperature in their vicinity, what physical mechanism causes this effect? Researchers proposed several possibilities. Dust in galaxies absorbs and re-emits CMB photons, potentially creating temperature decrements. Magnetic fields around galaxies might affect polarization, which could correlate with temperature. Free electrons in galactic halos scatter CMB photons through the Sunyaev-Zeldovich effect, known to create temperature distortions around galaxy clusters. But spiral galaxies aren't massive enough for standard SC calculations to explain the observed signal. Something more subtle must be occurring. Testing the foreground hypothesis requires detailed observations of many spiral galaxies, measuring how CMB temperature varies near each one. Simons Observatory and other ground-based CMB experiments will provide this data. If the effect is real and consistent, it becomes predictive. Given a galaxy's properties, mass, distance, orientation, star formation rate, we should calculate the expected temperature decrement. If predictions match observations across hundreds of galaxies, confidence grows. If not, the hypothesis fails. Meanwhile, we can't ignore exotic possibilities entirely. The multiverse explanation seems far-fetched, but it makes testable predictions. A collision between bubble universes during inflation would create a specific pattern in the CMB, not just a cold spot, but a disk-shaped feature with particular symmetries. Researchers search for these patterns in existing data. So far, nothing definitive has emerged. That doesn't disprove the multiverse, but it constrains what collision parameters are allowed if such collisions occurred. Cosmic textures and strings remain viable exotic explanations. These topological defects would create distinctive signatures in CMB polarization data, not just temperature. Planck constrained such defects but didn't rule them out entirely. Future CMB polarization measurements from Simons Observatory and the proposed CMB-S foreground-based experiment will push these constraints much further. If textures or strings exist at levels that could explain the cold spot, we'll detect them. If not, these explanations fail. The timeline for resolution spans the next decade. By 2030, we'll have Simons Observatory's full dataset, Rubin's first few years of observations, Euclid's complete survey, and Roman's initial results. DESI will have measured millions of galaxy spectra through the Eridanus region. CMB-S4, if funded and built, will be operating. This convergence of data from multiple independent experiments, using different techniques and covering different wavelength ranges, will narrow possibilities dramatically. Three outcomes seem plausible. First, observations might confirm that the supervoid plus foreground galaxies fully explain the cold spot within Lambda CDM, with the lensing discrepancy resolving as statistical noise or systematic error. This outcome validates our cosmological model and demonstrates that even unusual features ultimately conform to standard physics. Second, observations might require modifications to Lambda CDM, particularly regarding dark energy's behavior in underdense regions. This outcome revolutionizes cosmology, revealing new physics governing the universe's largest structures. Third, observations might demonstrate that the cold spot is indeed primordial, an extreme but allowable quantum fluctuation from inflation, with the supervoid being coincidental alignment. This outcome teaches us about probability, statistical interpretation, and the universe's capacity to surprise us. Each outcome advances knowledge. Each resolves questions that have puzzled cosmologists for 2 decades. And each opens new questions, because that's how science works. Answering one mystery reveals the next. The cold spot matters not because it threatens cosmology's foundations, but because it tests them rigorously. Our best models claim to explain the universe's evolution from microseconds after the Big Bang through 13.8 billion years of expansion. They predict galaxy formation, cosmic acceleration, large-scale structure. They've succeeded remarkably. But nature doesn't grade on effort. Every prediction must match observation, every anomaly demands explanation. The cold spot is cosmology's homework problem, and we're showing our work. Looking back across 2 decades of investigation, the cold spot has transformed from a curious anomaly into something far more valuable. It became a mirror reflecting cosmology's strengths and limitations, the certainties and the gaps, the power of observation and the humility required when nature refuses simple answers. We know the cold spot is real. Multiple satellites confirmed it independently. We know the Eridanus supervoid exists, mapped through galaxy surveys and gravitational lensing. We know foreground galaxies create temperature decrements around themselves through mechanisms we're still working to understand. These aren't speculations. They're measurements, reproducible and robust. What we don't know is how these pieces fit together. Whether the supervoid causes the cold spot through the integrated Sachs-Wolfe effect, or merely sits in front of it by cosmic coincidence. Whether foreground galaxies contribute significantly or negligibly. Whether dark energy behaves exactly as Lambda CDM predicts or requires subtle modifications. Whether that lensing discrepancy signals new physics or measurement uncertainty. This ambiguity isn't failure. It's honesty. The data genuinely supports multiple interpretations. Choosing one requires additional evidence we don't yet possess but are actively gathering. Missions already flying and launching soon will provide that evidence. Within a decade, we'll have answers. But here's what makes the cold spot genuinely important beyond its own resolution. The investigation itself advances every tool cosmology uses. Better statistical methods for distinguishing real signals from noise. More sophisticated simulations modeling cosmic structure formation. Improved techniques for measuring gravitational lensing and mapping dark matter. Deeper understanding of how foreground contamination affects CMB observations. Each of these advances, developed to solve the cold spot puzzle, applies broadly across cosmology. The next cosmic anomaly will be investigated with sharper tools because we honed them on this one. The next void discovered will be characterized more precisely because we mapped Eridanus so carefully. The next test of Lambda CDM will be more rigorous because the cold spot forced us to examine every assumption. Consider what we're actually doing when we study features like this. We're taking light that's traveled for 13 billion years, detecting temperature variations smaller than anything humans can sense, inferring the presence of structures spanning billions of light years, testing whether reality conforms to equations written by humans trying to understand creation itself. The audacity of this endeavor shouldn't be lost in technical details. The cold spot sits in the constellation Eridanus, a river in Greek mythology. Eridanus was the river into which Phaeton fell after losing control of the sun chariot, killed by Zeus for threatening to burn the earth. The constellation winds across the southern sky, faint and unremarkable to the naked eye. Most people never notice it. Yet in that direction lies one of the largest structures ever discovered, a void so vast it influences light from the universe's infancy. There's poetry in that. The universe doesn't announce its mysteries with fireworks. It hides them in subtle temperature variations requiring satellite instruments to detect. It places the largest known void in an unremarkable patch of sky most people never observe. Discovery demands looking carefully at what seems ordinary, measuring precisely what appears simple, questioning what seems settled. The cold spot won't revolutionize physics overnight. It won't require rewriting textbooks or abandoning Lambda CDM. But it might require adjusting that model slightly, sharpening predictions, acknowledging subtleties previously overlooked. These small refinements accumulate. They transform understanding gradually, adding detail to the cosmic picture we're assembling piece by piece. And if the cold spot turns out to be exactly what standard cosmology predicts, a rare but allowed fluctuation aligned by chance with a massive void, that answer teaches something equally important. It demonstrates that the universe contains surprises that aren't actually violations of known physics, just unlikely outcomes that probability permits. Learning to distinguish genuine anomalies from statistical extremes is crucial for any science dealing with unique events. You can't rerun the Big Bang. You can't create control universes to test variables. You get one cosmos to observe, one set of data, one chance to interpret correctly. The cold spot forces cosmologists to think carefully about what constitutes convincing evidence when dealing with such constraints. Those lessons transfer to every corner of the field. the void itself will outlast our attempts to understand it. Long after current satellites fall silent, after the Simons Observatory completes its mission, after we've moved to even more ambitious projects, the Eridanus supervoid will remain. A vast, nearly empty expanse of space, slowly evolving as the universe continues expanding. Galaxies that would have formed there never coalesced. Structures that might have been never developed. It's a hole in the cosmic web, not from destruction but from matter simply avoiding that region as structure formed. Future civilizations, if they exist, will observe the same void we're studying now. They'll see the same cold spot in their maps of the cosmic microwave background. They'll ask the same questions. Perhaps they'll have better answers, their physics more refined, their instruments more sensitive. Or perhaps they'll face the same ambiguities, the same challenges of inference from limited data. The universe doesn't arrange evidence for anyone's convenience. What matters is continuing to look. Continuing to measure. Continuing to test ideas against observation, discarding what fails, refining what succeeds. The cold spot is one problem among many, but solving it contributes to the larger project of understanding reality itself. Somewhere in the constellation Eridanus, light from the Big Bang passes through the largest void ever discovered, losing energy as it traverses that immense emptiness. By the time it reaches Earth, that light carries information about the universe's structure, dark energy's influence, perhaps hints of new physics we haven't imagined yet. We're learning to read those hints, slowly developing the expertise to extract meaning from subtle signals. The cold spot remains cold. The void remains vast. The mystery remains unsolved. But the tools grow sharper, the data more precise, the understanding deeper. That's how cosmology works. Patience rewarded with incremental progress, each observation narrowing possibilities, each measurement constraining reality. Eventually, we'll understand what created that cold spot in Eridanus. Whether the explanation is mundane or revolutionary, expected or surprising, it will be earned through decades of careful observation and rigorous analysis. That's the only way to truly know anything about the universe. You don't guess. You measure. You calculate. You test. You accept what the data demands, even when it's not the answer you wanted. The cosmos doesn't care about human preferences. It simply is, following laws we're still working to comprehend. The cold spot is one small piece of that enormous puzzle, but understanding it means understanding something fundamental about how reality operates on the largest scales. That makes it worth investigating, worth the decades of effort, worth the resources deployed to solve it. Above the Chilean Andes, telescopes scan the sky. In orbit, satellites map the universe. In laboratories worldwide, researchers analyze data, run simulations, test hypotheses. All of it connected to understanding a patch of sky in Eridanus where something unusual happens to ancient light. All of it driven by the simple human desire to know why the universe looks the way it does. The cold spot doesn't make headlines. It doesn't threaten Earth or promise revolutionary technology. It's just a cosmic mystery, waiting patiently for us to figure it out.